Hello everyone. I would like to introduce myself and my presentation for today. My name is Khalid Shboul. I am a PhD. I did my PhD at Kansas State University. So today I would like to talk about investigating the effect of U-wrap anchored doubly strengthened reinforced concrete beams with CFRP sheets. I would like to thank my co-authors, Professor Haidar Rashid and Dr. Fahd Salahat. So my presentation today will be divided into objective of the study that we did and a brief introduction. And then I will talk about the experimental program that we did and the results and discussion. And then I will conclude. So the main objective of this research program that we did is to see the contribution of the CFRP strengthening on ductility and serviceability when it is used as a compression reinforcement. So we are using the FRP as a tension reinforcement. In addition to that, we are adding the FRP sheet as a compression reinforcement. I would like to see the contribution and the effect of that. So as a brief introduction, the externally bonded FRP is widely used and accepted as the method of choice for strengthening the deteriorated beams and concrete structures. And that's the typical way that we normally look at the FRP sheets. The FRP composite provides stiffness and strength along the fiber direction in tension and compression, and they behave linearly elastic along the direction up to brittle material failure or rupture. So, however, there are some drawbacks in the FRP strengthening systems that sometimes limit the strengthening benefit. One of them, like it promotes the premature failure due to the debonding and then reduction of the member ductility. So if we are trying to mitigate all these, then we will get the maximum benefit of the strengthening system. So the unidirectional carbon fiber composite possesses similar or slightly lower axial compressive strength compared to the tension. So if we can use this fact in our strengthening techniques, then we can utilize the material more efficiently. So the ACI for 40.2 limit the extreme compressive stress in concrete under the service limit to 60% to avoid the serviceability issues. And that is clearly in the equation 10.2.8. So that might limit the usage of the strengthening material, and we cannot utilize all the material in our strengthening program. So the experimental setup that we did here is to use the FRP as a compression reinforcement in order to efficiently redistribute the compressive stresses in order to maintain this limit in order to enhance the ductility and the behavior of the beams. So what we did tested 8 beams, reinforced concrete beams. They were a rectangular cross-section, and they are all identical in the reinforcement. We used number 3 as a top and bottom reinforcement, and we use number 3 as shear reinforcement, space 2.5 center to center. And then we use a normal weight concrete to cast the beams. We intentionally used a high strength concrete. It was around 5.7 KSI, and lower compressive strength of concrete, it was around 3.5 in order to see the effect of that reinforcement or the FRP compression reinforcement on the lower concrete strength. And then we used the unidirectional high modulus carbon fiber sheet, the VRAR 770, for the tension and the compression reinforcement. So that's the experimental stress strain curve for the FRP material that we used. So the matrix that we did is, I said 8 beams. The first 2 beams, they were controlled without any reinforcement. It's just concrete reinforced beams, B1A, B1B. And then we did B2, which has tension reinforcement, just 1 layer at the bottom. And the B3, 1 layer at the bottom. And we added the compression reinforcement, but without anchoring the tension, without using any U-wrap or any kind of anchors, just to see the effect of the compression without anchoring that. And then the B4, we use the same reinforcement, like 1 tension at the bottom, 2 at the top, but we anchored the tension reinforcement by using the 3 single U-wrap bare shear span. We use the doubly, the singly U-wrap, just one sheet. For the B5, we use the same reinforcement, one tension at the bottom, two at the top, and we use 3 U-wrap, but in this beam we use double U-wrap. So the total would be 3 at each, and that would be 12. So the B6, we used one tension reinforcement and two compression, and we used 3 bare shear span double U-wrap. But this beam, it was a low concrete strength. This was for the lowest concrete strength. And then the B7, finally, we used one at the tension without any compression. It's just like a typical reinforced FRP beam. And then we tested all the beams under the 4-point bending, and that's the schematic of the test setup that we did. And we get some results and discussion here. So the first one, I would like to talk about the control beam. The both control beams, the reinforced concrete beams, show similar trend, and they are almost identical in behavior. And the black curve here, which is the FRP without any compression and without any anchorage. So the beam 2 underwent yielding and then failed in a debonding, intermediate crack debonding as expected. So the ultimate capacity was 13.68, and that shows 86% increase in the ultimate load capacity. So this is the picture of the failure mode. That's the intermediate crack debonding for the beam, and that's the typical crushing at the concrete ultimate fiber. So when we did the strain analysis that I would like to talk about more in the coming couple of slides, we found that the stress in the concrete 3.85 KSI, which is 12% higher than the limit of the ACI, which is the 60%. So even we are getting a more ultimate capacity, but we are violating that limit ratio that controls the serviceability. So it was like 12% higher, and then we are expecting adding more layers at the tension and even anchoring that FRP sheet that bring the ultimate capacity to be increased, that will increase the ultimate strain and the strain in the concrete. So we are getting, while we are using more material, more strengthening material, we are violating that limit, that percentage. So here's the idea. So the doubly reinforced concrete beams, we use the beam 3 that has 2 layers of the compression with no anchorage, and B4 that has 2 layers with the single layer anchorage, and the beam 5, just as a reminder, has 2 layers with 2 layers of anchorage. So we can see that the double strengthened beams almost they have identical behavior, but larger post-cracking stiffness compared to the beam B2, which was the control 1, and higher load capacity compared to the singly strength control beam. So they are also getting more load carrying capacity compared to the concrete one, the control 1, but has larger post-cracking compared to the beam 2, which has no compression reinforcement. So the beam anchored with 2 layers of U-wrap show higher post-yielding stiffness, while the other beams retain the same behavior up to the ultimate failure. So the ductility increase was noticed in the anchored double strengthened beams only, and we didn't see any increase in the ductility in the unanchored doubly strengthened beams. Even we are using the compression layer, but without anchorage, we didn't see a noticeable ductility ductile behavior. So the unanchored doubly strengthened beams showed the least percent increase in the ultimate loading capacity, about 4.6, compared to the control 1, the B2, with a failure load of 14.3 kits and deflection of 0.72. So here's the pictures for B4 and B5 after testing. The B4 and B5 showed 29.6 and 32 increase in the ultimate load capacity relative to the control. That's as a percentage, which is still a good amount of increase. And the percent increase in the ultimate deflection was 20.6 and 34.5 for the compared to the control 1. indicating a more ductile behavior observed in the presence of the compression layers and U-wrap anchors. So the U-wrap anchor shift the failure mode from the FRP debonding to FRP rupture combined with the compression sheet buckling in the constant moment region. We can see that the sheet buckles at the compression layer, and we have some FRP rupture material. So that's because of the shifting of the more anchorage and shift the failure mode from the debonding to this combined failure mode. So the strain analysis that we did is we obtained the moment, the service moment by dividing by an average load factor, and then we use that to obtain the stress in the concrete using Hottenstadt parabola. So the strain in the concrete at the top, at the surface of the compression FRP, and at the tension were measured using the strain gauges that we added in the beams. And then we did the strain analysis. We found that this is the strain. So this table and the graph show that the beam 2, we have 3.41, the 60% limit, and we are getting 3.85, which is higher. And then the B3, while we're adding more sheet in the compression side and anchoring, we are going from 3.74 to compared to 3.85, like 3% less. And B4, we are getting 8% less. And B5, we are getting 11% less. We are exactly matching the limit. And so we are getting a more ductile behavior while we are using the compression and the U-wrap anchoring. So mainly the compression FRP sheet bridges the crushed compression zone and redistributing the compressive stress over a wider region, even if this layer buckles outward. So the addition of the compression layer alone without any anchoring did not provide a significant reduction in the concrete surface stress. So the negligible benefit can be attributed to the intermediate crack debonding of the tensile sheet, preventing the full utilization of the compressive behavior. So the solution was anchoring the tension sheet with a single layer of U-wrap effectively improved the transfer of stresses between the FRP compression sheet and the concrete, leading to a more efficient stress redistribution at a higher ultimate load. So comparing the load deflection curve for B2 and B7, so we can see here the impact of the compression FRP layer on the behavior. So we can see the implementation of a single U-wrap just improve the strength by changing the failure mode from the debonding to the FRP rupture, and they have a minor influence in improving the post-cracking stiffness. The ductility ratio is enhanced due to using the U-wrap anchor, but the serviceability is caused to suffer since the strength is increased, admitting higher compressive concrete stress at the extreme fiber. So similar conclusion could be drawn to the beam 3 and B4, 5. So to see the impact of the FRP layer on the overall behavior, so we have here B5 and B6. So so it's expected to see a significant increase in the beam strength in case of the beam B5, having the higher compressive strength due to the delay in attaining the concrete crushing and compression FRP layer buckling. The beam 6 exhibited a much higher ductility due to the redistribution of the stresses in the presence of the compression FRP layers, and beam 6 benefited noticeably from the compression FRP with respect to serviceability due to its lower compressive strength, because we have lower compressive strength and we were able to increase the ductility by adding the compression sheet. So as a conclusion here, the FRP layer in tension and compression in the presence of the U-wrap could be significant improvement for the load carrying capacity and the ductility and serviceability. And the comparison of the doubly strength beam with a singly beam highlighted the advantage of the new strengthened configuration. So adding the compression sheet would enhance the behavior of the beams in terms of ductility and serviceability. This conclusion, we cannot see that without anchoring the FRP. So anchoring the tension layer in the presence of the compression played a crucial role in shifting the failure mode from the intermediate crack to the FRP rupture. And the anchoring technique contributed to a more ductile behavior and increased the ultimate flexural capacity of the beams. So the beams anchored with U-wrap demonstrated superior performance and proving the significant increase in the ultimate load capacity. So utilization of the compression FRP layers effectively distributed and transferred compressive forces within the concrete, resulting in an improved stress distribution and reduce of the concrete compressive stress. So addition of the compression layer when combined with the anchoring the tension layer showed a notable reduction in compressive concrete stress. So here, as a final conclusion, the experimental findings support the viability of compression FRP layers as a solution for enhancing the behavior of deficient concrete structure, especially when the ductility is a major concern. The use of this new FRP system and U-wrap anchoring technique combined together offer a promising approach to address structural deficiencies at a service level. So this could be a starting point for future research in the field of the compression FRP or utilizing the fiber FRP as a compression reinforcement for more ductile behavior of the beams. So I would reach the end of my presentation at this point, and I will thank you for your listening. Open it up for any question if you have.
Yes, can you please clarify what do you mean by a U-wrap? How did you actually do that?
The U-wrap?
Yes, can you explain
Yeah,
a
of
little bit
course.
to me?
I would like to go for a picture. So this is what I mean by the U-wrap. So the U-wrap is a mean of anchoring the tension FRP sheet. So normally that if we leave the FRP sheet without any anchoring, so the crack debonding will start at the maximum moment region at the middle and propagate toward the end, and that will make room for the sheet to debond and to fail without achieving the maximum benefit. So what we normally use, we use this mean of anchorage in order to provide like a confined space for that FRP to be attached and stick to the beam and to utilize the full composite behavior between the FRP and the concrete. So what I mean by the U-wrap is this FRP sheet that's like along the height of the beam that goes on the side and underneath the tension and goes up. That's what I mean by the U-wrap.
Can I ask another question? So
Yeah,
did you have also tension U-wraps as well?
I have a tension sheet, which is at the tension
bottom.
socket, and I have a compression sheet.
And then
So the
compression
U-wraps,
U-wraps.
they mainly anchor the tension sheet in its place, not they are not like a fully U-wrap, it's just a U-wrap as a U shape.
Okay, thank you.
Yeah, of course.
Yeah, I guess I'm a little confused as well. It seemed like that both the compression and the tension had to have anchored with the U-wrap.
No.
Just the tension?
So just the tension. So the U-wrap starts here, and we don't have a full wrap. It's just a U-wrap.
Compression side
It's just the sheet itself, yeah. It might be a little bit confined by using that spreader blade. That's the only confinement for the compression sheet. But we don't have any FRP sheet around that compression, yeah.
Okay, yeah, sorry.
No, just the tension.
So, I'm sorry again, so it comes like this, like a U shape from the top, right?
Like U-shape from the bottom.
From the bottom.
Yes.